you very much, all of you, for coming to the first colloquium of the EHU Quantum Center of this year. Today we have Professor Juan Gómez Cadenas, who will talk about Majorana's dream and the next growth. And it is a real pleasure for me to introduce Professor Gómez Cadenas. His curriculum is quite impressive. So after studying physics in the University of Valencia, he held a Fulbright fellowship at the Stanford Linear Accelerator Laboratory. He was a postdoctoral researcher at the University of California, Santa Cruz, a fellow and then staff at CERN, assistant professor at the University of Massachusetts at Amherst. He was also visiting professor at Harvard, University of Geneva, and KEK in Japan, and full professor at Valencia University and CSIC. And finally, as of now, he's an Ikerbasque research professor in the Donostia International Physics Center. So, he's an experimental particle physicist, and he studies the properties of neutrinos. Neutrinos are in principle a very simple and boring particle. They should be massless, and they have few interactions. However, since the last decades, we know that their properties break the standard model of particle physics. And indeed, Professor Gómez Cadenas has had a lot to say in this. So he has been part of the K2K and T2K experiments, which played a fundamental role in establishing that neutrinos have a non-zero mass, which breaks the standard model, and which was awarded the 2016 Breakthrough Prize. Now, since 2008, he leads the next experiment, which aims to identify if neutrinos are their own antiparticle, which we will tell us in a minute, at the Canfranc Underground Laboratory in the Pyrenees, in the border between Spain and France. He has received 2 very prestigious and competitive ERC grants to develop these experiments, and on top of that, he also writes novels and other books, and he's great in inspiring scientific careers of several people I know that were lucky enough to hear him when they were young, including myself. So, with this, I leave you with Professor Gómez Cadenas and Majorana's dream.
Thank you very much. Kaixo denoi. Good morning, everybody. So, after the very extensive presentation, oops, ¿se ha ido? Oops, let's put, okay. No sé por qué, se ha ido la... It's back? It's back? Maybe we want to put some power on just in case. Let's put some power on. Okay. So, there is another way of defining my career, which is that I've been dropping things along the way. When I started my PhD at CERN, I was working with all kinds of particles because I was working on the construction of the Delphi experiment. And the Delphi experiment was one of the 4 experiments at lab, where we did collisions between electrons and positrons, and then all kinds of particles would show up there, right? So then I moved to Mark II experiment at SLAC, and there I kind of specialized in leptons. So I dropped everything else except the light particles, and my first analysis was, I was telling Ivan, a search for lepton flavor violation. So these are kind of events that cannot happen, in which you start with E plus E minus annihilation, and then you end up with an electron or an muon, or an electron and a tau, or a muon and a tau. That cannot happen. Electron comes in pair, E minus E plus, mu minus mu plus, tau minus tau plus, but never mix. So we searched for those events and we didn't find them. But anyway, on that time, I was a happy guy who was working with 3 kinds of leptons, electrons, muons, and taus. Then I moved to CERN in the 90s, and I specialized in taus. So I did a lot of work on tau analysis, so I dropped the other 2 leptons. Then I moved to the NOMAD experiment, and then I dropped the tau. I just stuck to the neutrino tau, which was lighter than the tau. And then what I do these days is neutrino-less double beta decay experiment, so I drop also the neutrino. So I have basically nothing to talk about. Anyway, today I wanted to talk about not Majorana dim, but Majorana dreams. And maybe I should start by talking about Majorana. Ettore Majorana was a rare kind of genius. This kind of genius that Fermi, Enrico Fermi himself, a genius, said that Majorana was in the league with Galileo, Newton, and others. All right? So he was an absolute genial physicist, but he was a very weird person too. Most of the work he did in his life, he didn't bother to publish. It was too trivial for him. One example was he was very well aware of the efforts on neutron physics, but he thought all was just irrelevant, not interesting. But he came up with a notion that if you think about this, is really, really strange. Well, it comes from a previous notion. Around 1930 something, another genius, another weird genius, Pam Dirac, was looking at his equation and said, oh, my equation says that there are negative energy states. Now, this cannot be. Energy cannot be negative, but my equation cannot be wrong. Therefore, something is not fitting here, because my equation is true. Then I'll make the completely wild, completely crazy hypothesis that nature comes in two versions, matter and antimatter. Now, for us these days, this is familiar. But think on the point of view of a student in 1930, to which you tell him, look, look, there is not only matter, there is another copy of reality in which you have to inverse all the charges. What in heck? In fact, that existed, and that weird thing was the positron was discovered. But when the neutrino was not even discovered, but only speculated, Majorana said, oh, the neutrino has no charges. So notice that when I'm talking about electrons, I know that they are matter, and when I'm talking about positrons, I know that they are antimatter. Why? Because they have a label. Electrons are negative, positrons are positive, so cannot get wrong. But when I'm talking about neutrinos, what? Neutrinos are neutral, and there are no obvious labels that you can use to distinguish between a neutrino and antineutrino. So what Majorana did was to say, okay, if there are no labels, then there is no reason to believe that neutrinos and antineutrinos are different things. Maybe they are the same thing. So this is another jump in weirdness. Nature has not only produced matter and antimatter, two copies of reality for no good reason, but it insists that the only neutral copy of reality is both things. So by now, you should be convinced that all that bunch of physicists, they were pretty crazy. Okay? Now, the amazing thing about physics is that you test crazy hypotheses and they turn out to be true. So antimatter, of course, is true, and we know that actually the universe should have started in equal copies of matter and antimatter. Now, the question is, if this is the case, how come that we have a universe at all? Because imagine the original state of the universe. You produce exactly the same amount of leptons and antileptons, quarks and antiquarks. They annihilate each other. Nothing happens. Now we have experimental evidence that the universe exists. You will agree with me on that. So we need to find an explanation why something has happened to break that asymmetry. So this is the story I want to tell you. Let me start by very quickly telling you a bit of elementals. Electrons, you can make four types of electrons if you want. You can take an electron, which is left-handed. It has spins up. It rotates like that, except that electrons do not rotate. But anyway, let's keep it like that. And then we can make a parity operation and make it rotate like that, except that electrons do not rotate. But certainly, we can start with an electron like this, and end up with an electron like that. We call a parity operation. It's like we put a mirror on top of that electron. So we have electron left and electron right. And now the other thing that we can do is another kind of mirror that changes an electron into a positron, right? So we invert the charge. So if you think about it, we have actually 4 states. Electron right is the reflection in the parity mirror of electron left. Electron positive charge is the reflection in the parity mirror of the electron charge negative, right? Now, of course, now you can go ahead and make masses of the electron. How do you make a mass of an electron? You fill the universe with ether. This is what physicists do when they don't know what else to do. They put some ether on it, right? So you fill the universe with ether, but you know, ether is a name that these days is not well regarded. So we call it Higgs, which is even uglier, actually. You know, the ether boson would have been much nicer than the Higgs boson, which is like the Gómez boson. But anyway, it was Mr. Higgs who came up with the idea, so here we are. We are stuck with the ugliest name on the history of particle physics, Higgs boson. Now, what happens is that you have this left spinning thing, which has a friction against this ether thing, and then you end up with a right spinning thing. You put these 2 states there, you throw in some math, the theory is how to do that, and then you couple them with the Higgs boson, and you have what? A negative electron. So a negative electron you build up by using left-handed and right-handed states. Now you can also build a positron which is a positive electron, by coupling up left and right-handed states to the Higgs boson. Not difficult. So we end up, we reduce the 4 initial states that we had to 2, electron and positron, okay? And now they have mass. So we're happy. Now, we could do the same with neutrinos. We could say we take left-handed neutrino, couple it to right-handed neutrino, left-handed antineutrino, same thing, same operation. Except that you can notice that neutrino has no charge here, so no label. So you can save 2 states. You can say, okay, let me get rid of this state here and this state here, and just build a neutrino with just the conjugate state. Notice that you don't need 2 operations, because now the thing that transforms the parity operation and the charge negative to positive will collapse into something that we call simply conjugate operation. So this is what Majorana said. I don't need 4 states, I can do with 2, and then I build a neutrino out of this. Neutrino plus antineutrino, neutrino plus charge conjugation. Now if I take the charge conjugation here, I end up with the same operation, so the neutrino is its own antiparticle. Fine. Now this means what? It means that now I have a way to give mass to the neutrino. I will not get into the details here, but what is important here is that Majorana idea not only introduces something interesting, the fact that nature may have decided to give matter and antimatter properties to the same particles, but also a new way of getting mass, because you need 2 Higgs boson here. So in a way, Majorana was even wilder than it looks like, because he said there is a new type of matter. So neutrinos are not exactly the same than electrons in the way they acquire matter. So you could really truly say these particles are special. Now, it's quite a bit about, so we can actually summarize everything, like this is matter antimatter, and then we are fine here, right? We are fine here because we have labels. But when we have neutrinos, which are their own antiparticles, we fall into an Escher paradox. Here are 2 hands drawing themselves. So where is the neutrino, where is the antineutrino? We are trapped, okay? Now, we use that to produce this particle, which is its own antiparticle, and all of a sudden this becomes very convenient. Now, let's go back to the idea that the universe was made of identical amounts of particles and antiparticles. Again, Escher. Now, angels and demons. So in angels and demons, what you say is the angels that draw the demons, and they fill the space. What happens when you fill the universe with angels and demons? They fight, they annihilate, they disappear. Fine. Now you need to break this kind of doom. And how are you going to break it? By introducing a double agent. Now, if the neutrino gets the mass by interacting with two Higgses, a Higgs plus and a Higgs minus, and the neutrino is matter and antimatter, then it could be a heavy neutrino in the early universe who would decay to matter, electron minus plus Higgs plus. Or could decay to antimatter, electron plus plus Higgs minus. So the neutrino is injecting in the original game some amounts of electrons and positrons. This is what double agents do. They spy for one guy, they spy for the other guys. But all the double agents have an agenda. So you are never exactly balanced double agent. You, at the end of the day, decide for one group or the other. So in that particular case, the neutrino injected a little asymmetry, which we are trying to measure too, between matter and antimatter, a bit more of electrons than positrons. And then what happens? Eventually, electrons go to quarks. This is a different and interesting process, but we're not going to get there. These quarks annihilate with antiquarks, and basically all the original matter of the universe go to hell with the all original antimatter, except for the small asymmetry that the neutrinos injected. So if you want to think about it, the universe that we know, which is only made of matter, because it's only made of the matter that survived the annihilation introduced by the decay of the heavy neutrino, the universe we live is a very weird thing. Okay? Most of the universe went away, and the very few survivors of the greatest cosmic battle ever is us. This also explains why there is essentially no antimatter in the universe, and we know very well that. So, fantastic. This is the recipe to make the universe. You take a particle, that is its own antiparticle. You take a small asymmetry, and then pam, the universe. See? Now you talk to Ivan, and he puts some formulas on it, and it's all great. Okay? Now, from the experimentalist point of view, all this is very nice, but we still need to show that this is true. It's really the neutrino, its own antiparticle. And there is an experimental way to check that, which is what I call double or nothing. This is a famous game, right? You go, you bet with your cards. If you win, you get twice the money. If you lose everything. So the important thing here is you keep betting until you prudently go away. Now, in the case of experimental physicists, they just go under a mountain and they bet the next 20 to 30 years of their life. If they succeed, they get a Nobel Prize. If they don't succeed, they put a limit. Well, end of the story. So, my advice to you all students here, do not do this. By all means, don't do this, do something else. Go do quantum technologies, become rich, do economy, biophysics, but please don't. Okay? Don't go into the mountain, spend 30 years of your life just because you want to get the Nobel Prize. It's terrible. Then you get old, you still don't have the Nobel Prize, and there's 10 years more to go. Okay? But anyway, I'm going to explain you why in hell we are here doing what we are doing. So, why can you do this experiment? Very simply, because there is in nature a few nuclei. You know what is the usual beta decay? Beta decay is that I have a radioactive atom, and in that radioactive isotope, eventually a neutron will decay to a proton and emit an electron and a neutrino. This is the standard thing. It happens only once. We have many normal beta decays. But it can happen that sometimes two neutrons simultaneously go to electron neutrino, and then you have what we call standard double beta decay. This is a very strange process because it happens only when two neutrons do it simultaneously. It's suppressed by weak interaction strength square. So lifetime typical of this process is 10 to the 20 years. Now what is the lifetime of the universe, by the way? 10 to the 10 years. So how in hell do you get 10 to the 20? How in hell can you measure 10 to the 20? You only can because Avogadro number is very large. Okay, there is a lot of hell of matter in 1 gram of matter. Otherwise, we couldn't measure this. But we can actually. We measure this process, and it's a very interesting process for many reasons, but it's standard. Now, if the neutrino is its own antiparticle, then you can have an additional diagram. One of the neutrinos coupled to the other neutrino, you have this transformation, the neutrino, whoop, becomes antineutrino, flip the spin. And then you have a decay in which you have two electrons and no neutrinos. So this is what we call neutrinoless double beta decay. And this is what I do. As you see, you lose everything, the neutrinos, the electrons. Well, I am left with 2 electrons. All what I have in life now is 2 electrons. But I'm going to take good use of those 2 electrons, you will see. Okay? Now, so actually, this process doesn't happen in every isotope. It happens only in a few. It's a rare nuclear process, but I'm not going into detail because we will need 2 days to explain all that. What I am interested to tell you is that xenon is one of those processes. Xenon is the natural gas that you all know because it's in, you know, if you're old enough, you remember the cars with halogen xenon, right? Otherwise, you know, if you're young enough, you know that xenon is in the air with a small fraction. It's an old gas, yes? And xenon is a stable gas. That means that it cannot decay. Can you see here? It cannot decay to cesium beta because it has less energy. So this guy cannot really decay, except that it can make a double beta decay and decay to barium. So we know that the normal double beta decay of xenon exists. We have measured it. And we want to find if there is a neutrinoless double beta decay, in which case, again, we make a big discovery. Now it comes the bad news. This is the process in which I show you, it's here. This process in which one neutrino flips spin is what you need to do to produce a neutrinoless double beta decay. But flipping a spin is very difficult. It's very difficult because actually, if the neutrino would be exactly massless, you could not. The spin would be pointing exactly in one direction or in the other. And because the neutrino has a very light mass, you have a little bit of room to flip the spin, but it's very suppressed. So it turns out that the inverse of the probability of observing the decay, the inverse of the lifetime, is proportional to some factors, which we are not interested in now, times the mass of the neutrino. And to simplify the discussion, let me talk about the mass of the neutrino. In reality, this mass of the neutrino includes the oscillation term, but the mass of the neutrino square. So notice that the smaller the mass of the neutrino is, with the square, the longer the lifetime is. So it follows up that actually this is complicated. We're going to skip it. I'm going to stay here. I want to simplify the discussion to tell you this is where we are here. We are looking at the, we are able to say, so we can have 2 possibilities actually, realized by nature, depending on what is the structure of the mass of the neutrinos. And we are here, we want to get here. Now, in order to be sure that we discover or don't discover things, we should run the whole, this is neutrino, this axis is neutrino mass. So the harder the neutrino mass, the smaller the neutrino mass, the harder the thing becomes. Of course, if the neutrino has absolutely no mass or very small mass, then if we would be able to explore all this space, we would be able to say, okay, either I discovered it or not. Not quite, because there are regions where you don't have cross-section, you don't have probability. So this is an extremely hard thing to do, okay? And actually, it is so hard to do that the typical thing when you want to say that something is hard, you say that it's like searching for a needle in a haystack, right? Believe me, this is trivial. With our current apparatus, I can find you a needle with next. I will show you that we can find a needle in a cosmic haystack. The problem is way more difficult than this triviality. This is simple. Let me show you. Let's start by asking neutrinoless double beta decay, remember? 2 electrons only, no neutrinos. So if I add the energy of the 2 electrons, and I have a perfect detector, then it's always the same energy. It's a spike. It's a totally monochromatic decay on the sum of the 2 electrons. Each electron has their own energy, but the sum, in the case of xenon, 2.5 MeV, end of the story. So the experiment is trivial, right? You go to the shop and tell the shopman, please give me a perfect detector. And the guy asks, what is the perfect detector that you need? And you answer, a perfect detector that measures perfectly the energy. And he gives you the detector. Now, you put the detector in your system, you fill the perfect detector with xenon, and if you see a single event with 2.5 MeV exactly, bam, done. Because it's a perfect detector, it has no error. So it will measure precisely, exactly the energy of the event. One event, you're done. So simple. The problem is that there are no perfect detectors, yeah, sure. So the guy gives you something that measures a little Gaussian. Maybe very narrow Gaussian, but a little Gaussian, because errors are Gaussian when you are lucky. So you're going to get background, maybe from the 2 neutrino mode, or from other backgrounds. So things will creep into your non-so-perfect detector. But now you have a second possibility. So say, oh, give me a perfect planet. What is a perfect planet? A planet that has no radioactivity on it. Okay? And the guy says, no, sorry. All what I can give you is Earth. And Earth happens to be a very radioactive planet. In case you don't know, radioactivity is killing you. Actually, it's not killing you because you are very well adapted to it. But these walls are shooting you photons, and muons are dropping onto your head by the millions. So the only reason why you are alive is because life is, able to adapt very well to all these kind of nasty things. So Earth is radioactive. Now, the second bad news that I have for you is that backgrounds, so because Earth is radioactive, means that in your not-so-perfect detector with your very non-perfect Earth, you're going to get radioactive backgrounds inside, yes? And then, I say, okay, not a problem. What do we do, Ivan? And Ivan says, oh, subtract the background, that's it. So we subtract the background. We are done. No. And who is the bad guy now? Poisson. Poisson. This guy, Poisson distribution, turns out that if you say, okay, my most likely mean event is 1, it turns out that you have a probability of having 3. So when you do subtraction error, you have a subtraction error, and you have to live with that. And this subtraction error kills you. So, what is... Now, speaking on backgrounds, in case you thought I was exaggerating, here you have plenty of them. So you have the uranium and thorium, natural chains, and they end up in an incredible huge mess. And by the way, they are long. They live like the universe, 10 to the 10 years. Okay, if we make the experiment in another 10 to the 10 years, maybe we're all right, they will have decay. But now it's too soon. We need to wait another 10 to the 10 years, maybe. Okay, how do you do this? Let me give you the order of magnitude. We want to measure lifetimes. We have already looked at the 10 to the 26 year lifetimes and found no signal there. We want to get to 10 to the 27, maybe 10 to the 28, to see if the signal is there, all right? Remember, lifetime long means neutrino mass small, because neutrino mass is pretty small and there is a square. the lifetime becomes very low. We want to explore 10 to the 27, but the background is 10 to the 10. So there is 17 orders of magnitude. What do I mean? The background is 10 to the 10 years. So there is 17 orders of magnitude in order of magnitude more background than signal. So what is 17 orders of magnitude? Okay, take La Playa de la Concha, Concha's Beach. Let's make a calculation. Let's assume that we stretch La Concha to make it 70 kilometers long. Okay, so practically La Concha goes from Donosti to Bilbao. And then we make it 1 kilometer wide and 1 kilometer depth. Then we get into the 17 grains of sand. And then we say, find me 1 grain of sand in this beach from Bilbao to Donosti, which is blue. Here you are. I told you that the needle on the highest tag was a trivial problem. This is a problem. This is what I call the Majorana beach. And this is the problem, our problem. Okay, this is, do you understand now why I'm telling you do not do this? Is that clear for you? So how in hell are we going to try to do this? Now, this plot should tell you what I told you about backgrounds. Suppose that my only problem, that I have zero background. Again, let's go back to the perfect detector that I got in the shop. If I have zero background, actually, because the detectors are not perfect. Let's imagine that I have a background which is only 0.05 counts in the region where I'm going to, remember, I'm going to look my signal in something we call the ROI, which is where the signal should be. It would be a spike, except a small Gaussian. Imagine that my background per ton of detector and per year is 0.05, nothing. Well, my curve still saturates. Backgrounds always kill you. But I could get to 10 to the 28 only in 50-ton years. So if I make an experiment with 1 ton of mass, I just need to wait 50 years, a couple of generations, who cares? I mean, people build the cathedrals like this. So if they could build the cathedrals, we could do the experiments. Or we maybe go and say, okay, well, let's do something different. Let's put 10 tons and then wait for 5 years, or 5 tons and then wait for 10 years. See, don't do this experiment. Now, this is 0.05. Now, suppose that you have 0.1. It gets worse. But suppose that you have just 1 count. Then, boom, it goes worse. And then suppose that you have 5, boom. So, conclusion. You need to design experiments that in the scale where you're going to look at have basically no background. And this is why this is so damn difficult. Because reducing backgrounds in an atmosphere where you are totally surrounded by backgrounds is hard, difficult. All right, so this is next. Now, there is a few guys that, I mean, at this point of the talk, 12, 15, I could finish. We could all agree, guys, this is impossible, let's go home. Right? Let's do something better, use our time in a better way. But no. You know, there are a bunch of people who say, no, I'm going to do the experiment anyway. There are a number of possibilities. Because of time, I'm going to tell you only one, which happens to be mine. Sorry. So one thing you could do is you go to the shop and say, oh, give me a big tank, maybe 100 kilograms or 1 ton or 5 tons. Okay? This big tank we fill with pressurized xenon. Because we know that xenon is going to decay. Remember, xenon is going to decay and 2 electrons are going to appear. If I make gas, these 2 electrons are going to move in the gas. And now I can put an electric field. The xenon is a noble gas, so the electron will ionize the xenon and will eject little electrons from ionization. Now I drift my electrons one side, the barium atom to the other side, and these electrons that I'm drifting, once they get to the anode, I accelerate them a little bit, and each electron produces light. And now my detector has sensors for light and sensors for light. These are pixels. So these are used to transform this into this. So what you can see here is an electron that propagates to the chamber, And I transform the ionization electrons into light. I record light with pixels of light, and then, which are called silicon PMs, for those of you who work with them. And then I make the reconstruction of a single electron. And now, why do I know that this is a single electron? Because an electron which propagates through gas is a MIP. Ionizes, 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 always losing about the same energy, until when it's close to the endpoint, zoom, it loses all the energy in a single go, the black peak. And this is this little head. So this is like a worm with a head, yes? Okay, this is my picture, and then on that side I measure the full energy of the event. So I have a detector that measures energy with very good resolution, where this plot says is that you can measure with extraordinary good resolution in xenon the energy. In theory, now you need to prove it. And you can also make the track. So in principle, we have a nice detector. Now, neural networks are very much in fashion, right? Artificial intelligence, deep neural networks. Now let me check, let me train your natural neural networks, N. Okay? I'm going to train your natural neural networks with only one event, not a million of events. Tell me who's an electron and tell me who's two electrons here. Very, very, very easy. One head, nothing, single electron. Two heads, two electrons. So, if I show you another plot, I will show you in a second, which you will tell me your natural neural networks will tell me what you see. I have trained you with one event. Okay? This is in theory what we can do. Actually, the nice thing about nowhere detector is that backgrounds come from outside. And almost everything that comes from outside will be suppressed, except photons that hit the gas and produce a single electron. So at the end of the day, my game is the electron has to trick me into pretending it's a double electron, and the energy has to be right. So the level of suppression, you can imagine, is very high. Now, of course, in practice, I am not having this beautiful electron that you get in a Monte Carlo, because when you drift the electrons, they diffuse. So I am getting something uglier, but we'll get there. So before, let me show you this picture. This picture is my mentor and great friend, Dave Nygren, inventor of the TPC, the technology in which we are based. My other mentor, James White, at the time the greatest expert ever in high pressure xenon TPCs. My student at the time, now he's already a thesis professor, Justo, and myself with no white hair. And that was 15 years ago in Berkeley, and we had a meeting and we came up with the idea, oh, we could build a detector. And you know, these Americans, we said, oh, let's do it. So we did it. So this is like 12 years ago. Again, no white hair. First prototype, like this. Francesc Monraval, now an associate professor at the DIPC, at the time very young. This guy was James' student, and he was also a lieutenant in a nuclear submarine before he joined us. Quite a guy. Next detector, next white. We put it in Canfranc. This is only 10 years ago. By the way, when 15 years ago we said, we're going to build this detector in Canfranc in Spain, it's going to be built, the answer was from a lot of the community, that will never work. But why not? Look at the ideas. If it could work, the Americans would have made first than you. And then the answer, well, but the Americans are making it with me. Well, it took a while to convince people, right? So this is this detector is called White because in the honor of James White, who died. He died actually almost the very same day that I got a letter from the European Research Council saying that I had got an advance grant which allowed me to build this detector. Without the grant, I could have never pushed this project forward because we were running out of money. This is Spain, I don't need to explain you. Well, this is the Basque Country, which is not exactly Spain. At least funding-wise, there is a big difference. But at the time I was in Valencia, it was really difficult. The ERC saved my day. Of course, if you ask me whether I believe in miracles, I will tell you the same thing that the Galician people say when they are asked if they believe in meigas. Existir no existen, pero verlas, haylas. So, miracle happened. We built the first real detector. That was 10 years ago. And then we did a number of interesting things. Notice that the signal of we are looking for is here. And what do you see? This is the background. What you see is very pretty, right? There's a pretty hole when we do our analysis, saying, okay, if the signal is here, we're going to see it. So that was our demonstrator. We also measured the normal mode, the 2 neutrino mode, which is 10 to the 20 years, but we did measure. So we thought, okay, we are in position to build the next detector. And the next detector is called X100, is this monster. Now it's a bigger thing, yeah. You can see the photomultipliers that integrate the energy, and the pixels, the silicon PMs that allow us to make the tracks. So this is a 1 meter by 1 meter side photographic camera of electrons, right? And this is the drift field to drift the electrons. And here, tell me what are the single electrons and what are the double electrons. Easy, right? So, single electrons, double electrons. By the way, these are not Monte Carlo. These are real data. And you will say, what? If you have seen real data, double electrons, where is your Nobel Prize? Well, I need to see double electrons exactly at 2.5 MeV energy. But I have a way to produce double electrons to convince myself that they exist at lower energy. And this is the trick. And I will show you that in a second. The point that I want you to see is that once the double electrons show up, we can see them very well. So, this is data from X100. This just comes from the detector that is operating last week. And when I tell you that we have very nice energy resolution, I am not lying, right? So you can see all the radioactivity peaks. And if you put in logarithm scale, here is a radioactive peak on thallium. This is where our signal is. This is our excellent resolution. And this is, again, the very nice resolution that we get. And this is the kind of events that we are showing. Again, 2 electrons. Well, why 2 electrons? For this reason. Because thallium can have what we call the double escape peak, okay, in which 2 photons escape and you have an annihilation electron-positron. So if we go to this peak, we know that we have electrons and positrons that we use to demonstrate that we can measure electrons and positrons, and then we search here. So what we are doing today is searching for the signal, but we already know, because we have 100 kilograms of the detector, that there is no way that we're going to find it. Because our sensitivity is of the order of 10 to the 26 years, and we know that the signal is farther than that. I mean, there is a very small margin, we could be lucky. But the reason we are working is not so much to be lucky, but to understand the detector. What does it mean to understand the detector? It means we need to reduce the radioactivity because we need to go to the next order of magnitude, put 1 ton, and wait 10 more years, which implies more radioactivity. So our problem now, all what you see here is just background scales. So this is what we expect from the silicons. Okay, we are now thinking how we suppress this. Even if this appears to be very big, look at the rate. This is counts per year. So it looks like, oh, these guys are full of background, right? No, no, no. Our counts are a fraction of count per year. But we are obsessed with the fraction of count per year. We need to reduce it to 0. Okay? So now I want to, not to make the thing much longer than that, how are we going to do that? Slightly changing technology. For instance, we're going to replace the photomultipliers that are at the end of the detector by a barrel of optical fibers, which have less radioactivity. They are nicer. Then we're going to make the tracking plane, which now have little silicon PMs of 1 millimeter square. We're going to make them of 3 or 6 millimeter square, so we can also measure the energy with the pixels. And we're going to do a number of tricks. Basically, we're going to make the detector twice as big. And we're going to put a lot of mass. So the idea is that we're going to end up with this kind of detector, which is 1 ton. Same idea, 1 ton of xenon. Now, what is important for me to understand is that if I have a detector like NEXT, which has 100 kilograms and a background of about 1 count per year, it's not enough just to go to the shop and buy 1 ton of xenon. The background needs to be reduced to a fraction of a count, or I will do nothing, because background subtraction will kill me. Clear? So our next step now is to improve our detector, to build it larger, and to keep going. This is another view of the detector. A few questions that I will drop very quickly to you. If all what I am expecting is 0.1 background events per year, how do I measure this? How am I ever sure that I know how to measure 0.1? If you have good ideas, let me know. We can write a paper together. All right? We don't know how to do that. By the way, we don't tell anyone. We don't tell the theorists. No, we know how to measure that. Yeah, sure. 0.1. Oh, no idea. All right? The other thing, guys, is that I'm talking about xenon all the time, and none of you have told me shit. I mean, xenon has 3 isotopes at least. 135, 136, stable, 134, stable. The only one that makes double beta decay is xenon 136, which is the heaviest. And to do the experiment, I need to enrich the xenon, which means I need to separate xenon 136 from all the rest. And guess where do you do the xenon 136 enrichment? Which country does it? You need a nuclear centrifuge. The kind of stuff that you use to do an atomic bomb. Sounds familiar? Who does that? Russia. And what happens now? We are in war with Russia. So can you get xenon 136? No. So how do you get the xenon 136 if you bought it before? Okay? Now, fortunately, there is 1 ton of xenon 136 enriched in the world. We have 100 kilograms, the Americans have 200 kilograms, the Japanese have 800 kilograms, and we are very close friends of the Japanese. And we are becoming even closer friends. You know, this is a real love story. So, in order to make 1 ton xenon experiment, you need to make a truly international experiment with Japanese, the Canadians, the Americans, blah, blah. So now you understand that if you want to come to visit Canfranc, you're welcome, we can organize it, but we need to talk before, because easy is that I am in Canada, in Japan, or somewhere else, making friends, right? So, this is the kind of things that we dream. Eventually put not 1 ton, remember 1 ton is 50 years, but 4, 5, 6, 10 tons, which implies to build a lot of detectors. And this is what we call the multi-module approach, but kind of don't tell that it's also multi-money approach. Like, yeah, multi-module approach, you just give me 100 millions, I'll do that for you. By the way, it's very cheap compared with the amount of money that everybody's spending in artificial intelligence. All right, so don't come, let's not get there. Anyway, before I finish, let me give you a final kick. Now, I told you that we want to go to many tons of mass. And some of you should already be telling me, come on, what are you talking about? Backgrounds are going to kill you. I mean, 2 electrons is fine, energy is fine, but if you keep going on and you need 0 background, backgrounds are going to kill you. You need something extra. Now remember that when xenon decays double beta, what does it do? 2 electrons and what else? A barium. A barium isotope, yes? Now, this is what happens. You make barium, and now what happens if you take the electrons one side and then take the barium the other side. Now, the barium drifts on your field to the cathode. Suppose that now you put a trap to grab this barium, and you invent a way to find this atom that is trapped. Well, this is what we call bold. Bold means valiente, and you need to be bold or crazy to come up with the idea. So the idea is the following. We make a net of atomic molecular traps. So these are molecules that have a ground, and when they don't have a barium inside, if you excite them with a laser, it gives you no answer. But if they grab the barium, you close a circuit, and then a molecular circuit, and then when you illuminate them, for instance, with a blue laser, they can give you a green answer, for example, or they can just bright. So the trick now is that we drift the barium atom to the cathode, we examine the region where we know the barium is there, we know from the position of the electron where to look for, and we see if we see a single point where a molecule has grabbed an atom. This is what we call barium tagging. The ideas are pretty crazy, but Fernando Cosío from this university, myself and Rosanne Genet, which at the time was at Harvard and now is in Massachusetts, in Manchester, we proposed to the ERC a program to develop this, and they gave us the money. So they gave us a synergy grant to try this. We have been 4 years hard at the thing. We have made a lot of progress. My guess is that in another 10 years or so we are done. All right? Anyway, 10 years is fine because this is what we're going to need to build the large detectors. So guys, my guess, I'm only 65. My guess is that with any luck, in 10 years we are okay. So 75, maybe I will be able to see the discovery. Now, believe me, I don't give a damn about Nobel Prizes. But I would really, really, really love to see, to demonstrate that the neutrino is a Majorana particle. This is what we would like to see. This is the signal we are looking for. 2 electrons and a bright molecule shining. And this is our bold proposal, which is where I leave you with all this blah, 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 which is basically telling, give me the money, and give me the time, and please, each one of you, I want to thank you very much for all this very abundant audience. Among all the older guys, nothing to say, thank you very much. Among the very young guys, please don't believe a word. Go do something else. But if you're crazy enough and you want to come working with us, talk to Lady. She will explain you, that because we are crazy enough, we have a lot of fun at the APC in Donosti. Thank you very much.
Thank you very much for the very nice and broad overview. So I guess we have time for questions. Don't be shy.
Hi, thank you for the talk. Very fascinating. I have a question about this tagging, barium tagging, because everything seems to be non-perfect. Here, do you have other signals that the molecules can give you that are not because they're trapping baryons?
Yeah, that's a very, very smart question. Now, here, there is 2 answers to that question. The first one is, of course, the molecules that Fernando and company are developing are pretty selective. So they will not grab anything. But actually, they are not perfect. So they will grab barium, but it could also grab, eventually, radium. So actually, this is an advantage for us. Because if we want to calibrate our molecules, we want to be sure that we are seeing the signal. We don't have barium easily, but we can use radioactive radium to calibrate. But now I need to answer your question. If it could grab something, how do I know that things are as I say? So the first answer is that actually inside a pure xenon TPC, where you are filled, all the materials are ultra radio pure, and you are filled with xenon, actually there is not much around. But the most important answer is not that one. The most important answer is what we call the delay coincidence. So, as we have seen, we have an event, 2 electrons. Something can fake the 2 electrons. A signal with barium shining. Something could fake the barium. But both at the same time is very difficult. This is the way that the neutrinos were discovered. When you got the neutrinos coming from a nuclear reactor into your scintillator, you had a first reaction that came from the neutrino deep scattering, so you had an electron. And a lot of stuff could fake that. But then you produce a neutron. The neutron walked a little bit and then got annihilated and produced 3 photons, and you had ting, ting. We have exactly the same. 2 electrons, you wait. You know when the barium is going to go to your cathode. So you only open your gate to let the barium enter in that moment, not before. So nothing else can go in. And then you know exactly where to look. So now the background has to fake the 2 electrons, and precisely in the molecule where you have predicted that it is the barium. The probability of this, 0. Delayed coincidence, that's the trick.
More questions?
There's one over there. If the question is going to be how much we're going to pay you, not much.
Yeah, so I actually had 2 questions. The first one, you talk about a heavy neutrino in the beginning. Mm-hmm. What's the relation between that and the neutrino itself, or why is it a heavy neutrino? And also, since most of your, I guess you said most of your work were reducing background, could this be applied to other experiments that also have a problem with background, or is the technology only for this kind of experiment?
All right, so the first question is that the heavy neutrino present, which is, by the way, a speculation. We don't know until we demonstrate. And actually, doesn't need to be, the heavy neutrino, for the time being, is a hypothetical beast, all right? And hypothetical beasts are, theorists, believe it or not, they preach the existence of hypothetical beasts, heavy neutrinos, unicorns, dragons, and they get paid for that. So this hypothetical beast could have been in the early universe and would not be longer around. Well, the neutrinos that we have now are light neutrinos, but you can connect both of them, and actually you can show that if that neutrino was a Majorana particle, this neutrino is a Majorana particle. All these magic tricks, talk to him. He'll show you how to do that, and he will convince you amazingly. All right? Now, when it comes to background subtraction, we are not the only experiment searching for neutrinoless double beta decay. Others try. Everyone is plagued by the same problem of background, but different experiments try different tricks. And this is important because if we make a discovery, it's going to be a few events. So you don't want to be the only experiment that makes a few events discovery and say, okay, you want somebody to check. So there's at least 3 different technologies, one based on xenon, another one based on germanium crystals, another one based on molybdenum bolometers, which are developing more or less at the same time, and we all expect to have possibilities of discovery in about 10 years. So different ways of attacking the backgrounds are also interesting because the background affects in a different way different detectors. Does that answer your question?
More questions?
There's a question. Ivan, over here.
Thank you.
do the current limits on charged Higgs, how do they, if they become more stringent,
Right.
would that sort of demotivate this?
So I don't have in mind the precise number of charged Higgs limits, but I don't think they are limiting at all the process, because the process actually happens in a virtual shell mass. So you can, you have plenty of room for that. I think that the limit, the real limit, you are more limited by the neutrino mass itself than by the Higgs mass limits. So when you factorize that into all these numbers, including oscillation number, this is not especially something that. Also, by the way, this is one process. This is the kind of a standard process, which it's still totally valid, but you can imagine 100 different ways to make the neutrinoless
Right,
flip.
so you don't necessarily
course.
rely on a charged Higgs.
So to get mass, you need to get the Higgses there. But you can keep always pushing the Higgses, the charged Higgses up, and nothing is going to kill you, as it happened with the neutral Higgs first. Right?
Okay.
More questions?
Don't be shy.
Hi. I'm sorry. In the double beta decay, how does the flip works? How do you get two neutrinos from two electrons from one neutrino? How does?
These guys are smart. They come with the interesting questions. This is an interesting question. How does it do? Because it can. That's the answer. It's not a trivial answer. If we start, so this is the interesting point. Now, let's recall. The original neutrino was a very uninteresting thing. It had no mass, no charge, nothing. So it was like, why do you want to do neutrinos? I mean, neutrinos have nothing to offer you. Then we discovered neutrino oscillations. Well, I spent 20 years on that game, by the way. And after 20 years, I should have learned, like, go do something else. No, man. All right. We discovered neutrinos have mass. Now, massless neutrinos can only spin in one direction. So if you are a massless neutrino, your spin is like in your direction, right? You only spin like this. And then if you are anti-neutrino, you spin like that. And there's no way you can flip. So a neutrino without mass cannot flip. End of the story. But if you give a mass to the neutrino, then helicity, which is the property of having a spin along the zone, and what is the other name? Helicidad and chirality. Helicity and chirality are not the same thing. Which means the following: because you have a mass, now you have two states. One state is very so if you have a mass like the electron, you can spin left and right. Remember the first transparency? Because we have masses in the electron, I can have a mirror like this and another like that. I can have electron spin left and an electron spin right. Actually, the electron is mostly left-handed because it has a very small mass. But I have room for the other electron just because I have a mass. And if I have a mass, the electrons are not forced like that. You have two states. Now, neutrinos have even a smaller mass. So they have very, very, very tiny space for the other one, but it's there. So if you can have the two states, then you can have a diagram in which one spin goes to the other one. And that's it, you flip. The question is then, with probability? Very small. Proportional to what? Actually, to the probability of flip needs to be proportional to what? To the mass. Mass 0, 0 probability of flip. Mass something, some probability. And if the amplitude is proportional to the mass, the cross-section or the lifetime is proportional to the mass squared. Therefore, probability very small, but probability is there because you can flip, because you have mass. Okay?
Any further question? If not, we can thank the speaker again, and thank you everybody for coming.